So, here is a quick recap of what we discussed in the last class. So, we are talking about the equipotential surfaces, right. First we took was point charge. So, because of point charge, positive charge field lines will be outward, and equipotential lines in 2 dimension we got circle, all concentric circles having different potential. So, because of point charge we got formula V is equal to kq by r. So, for a fixed value of potential you will get circle, and if you change the value you will get different circle, right. So, as you move from here to infinity, at infinity you will get equipotential surface having potential 0. So, when I talk about the equipotential surface somewhere here, potential at r is equal to infinity will be 0, right, and somewhere here say potential for this one, this innermost one, assume that if this is say 10 volt, the next one say 20 volt, then this one say 30 volt. So, as you keep going out, potential is increasing, right, but at infinity potential has to be 0 and r tending to r is equal to 0, potential has to be infinity. So, that means instead of you are getting 20 here, it would be like this. So, this will be this inner one will be, if I assume this to be 30, then this will be 20, this one will be 10, similarly this will be 5 volt, and this way potential will be distributed in space. So, all equipotential surfaces will be spherical, and on 2 dimension they will be concentric circles. This is for point charge. Then we talked about infinite linear charge distribution. If charge is distributed over line, then equipotential surfaces will be cylindrical, because that cylinder will be at same distance, every point on the cylinder will be at the same distance from the distribution. So, same way if I say this is say 30, this will be 20, like that, it keeps decreasing, right. Then if we have got uniform field, that might be created by some infinite sheet. Then the equipotential surface will be plane. So, in this situation we got planar equipotential surfaces. So, this is what we discussed in the last class. See, if I take 2 positive charges and I want to draw equipotential lines on xy plane, if I want to draw equipotential lines. So, see how the equipotential lines will be. So, these lines are representing equipotential. So, electric field in a space we already discussed, it will be something like this, and if I draw equipotential line keeping potential fixed, then these lines will be something like this. We can find the mathematical expression for these line by considering one of the charged particle. Say if this is y axis and say this one is x axis, right, and for a given value of potential I want to draw equipotential line on xy plane. So what I can do, if this is x axis, this is y axis, the coordinate of this one will be x comma y, right, and let the separation between them is a. So what I can write, potential at this particular point. So to write the potential at this particular point, I can write potential at that particular point is k q divided by under root x square plus y square. Because of this positive charge at this particular point, you can see this separation is under root x square plus y square, right. So k q divided by under root x square plus y square, right. This is the potential created by this charge at this particular point. Now because of this charge at this particular point, potential is k q divided by, now separation is, this distance is y only, this distance, remaining distance, if this is x, this total is a, this remaining distance will be a minus x. So this distance is a minus x, this distance is a minus x, I write it here, and this distance is y, I can find out this distance. So substituting this distance over here, I will get the potential produced by this charge at this particular point, that is a minus x whole square plus y square. For a given value of potential, this quantity will be constant, and if I simplify this one, then I will get the relation between x and y. If I plot that relation, I will be getting all these lines. I hope it is clear ki how we are drawing all these lines. At any general point, I write the potential, potential is a scalar quantity, positive charge will produce potential, this charge will produce potential, due to both the charges potential produced, if you add you will get the total potential. Now you want to draw a particular line which correspond to a particular potential, for example 10 volt. So if I substitute 10 volt here, now you can see I am getting relation between x and y coordinate. If that relation I plot on xy plane, then I will get these equipotential lines. So I hope it is clear how we have drawn all these lines. See once again, so very near to the charge it will be something like this. As you go away from the charge, these will be joined, and there will be one more line, I am drawing it separately, it will be something like this. Right. So actual equipotential lines will be something like this, right. I hope this equipotential line on xy plane due to two positive charges are clear. What if I take second charge particle negative? So one charge particle is positive, another charge particle is negative. In previous case you can see as both are positive, you won't get any point at finite distance where potential is 0. You won't get any point at finite distance from charges where potential will be 0, because both the quantities are positive, right. But if I take one positive, one negative, let us see another one. If I take one positive charge and another negative charge, the potential exactly at middle will be 0. This will produce positive potential and this will produce negative potential, and they will get cancelled out. So exactly at midpoint potential will be 0. Similarly, if I take any point on the bisector, I take any point on the bisector, everywhere potential will be 0, because at the point on the bisector, that for that particular point this distance will be equal to this distance, this will produce negative potential and this will produce positive potential, they will cancel each other, right. Now visualize a plane passing through bisector, a plane passing through bisector. So if I keep two charges, one positive and equal amount of negative charge I place here, and I take a plane passing through bisector perpendicular to the line joining, every point on the plane potential will be 0, because this separation is equal to this separation, this is producing, this negative charge is producing negative potential and this positive charge is producing positive potential, and net potential will become 0. So now I want to draw equipotential line. One thing is clear, that there will be a one line, a straight line on which potential will be exactly 0, right. Let us see how you will get the equipotential line in a space. So these are the equipotential line. Let us have the look once again. If I assume, just assuming that say potential here is 10 volt, for that particular line potential is coming 10 volt. As you keep moving this side, potential keep reducing, right. So from this 10, now say it become 7 volt, this has become 3 volt, right. Exactly at midpoint or exactly at bisector, potential will be 0 volt. As you move towards the negative charge, potential will become negative. So this will be representing say minus 3 volt, somewhere here it will be minus 7 volt, and similarly somewhere here it will be minus 10 volt. So as you go from this charge to this charge, you can see here that equipotential line will intersect the line joining these two, which have the potential 10 volt, then this is 7, then this is 3, exactly at mid it is 0, then it start becoming negative minus 3, then it will be minus 7, then it will be minus 10, right. So we have taken two positive charges and we have drawn equipotential line in a space, one positive, one negative, we have drawn equipotential lines in a space, right. So equipotential line concept is clear. You can see some point here itself that I will be discussing later. Look at this line, this is representing the field line, the yellow one is representing the field line. Electric field lines are always perpendicular to the equipotential line. So this angle is 90 degree. If I take another charged particle, very small charged particle, and I move that charged particle along this line, as delta V is equal to work done by external divided by Q naught. If I use this basic definition, then as I move along the line, potential is not changing. As this quantity is not changing, work done by external agent to move charged particle along equipotential line or along equipotential surface will be 0, right. One point. Another point, equipotential line will make 90 degree with the electric field lines at every point. Here also you can see this angle is 90 degree, this angle is 90 degree. Anywhere you take the angle between equipotential line and electric field line is 90 degree. Similarly, you can see here, right. So these property we will separately discuss. I hope concept of equipotential lines are clear. Now, let us see the property of equipotential surfaces. Just now I told that lines will be perpendicular, equipotential line or equipotential surface will be perpendicular to the electric field, right. So, to move charged particle on equipotential surface, you need not to do work. So, first point, no work is done in moving a test charge from one point to another on equipotential surface, because the basic definition of potential difference between 2 points when a test charge q naught is moved is work done by external agent to slowly move test charge from point A to B. So, if there is no change in potential, work done by external agent will be 0. If this quantity is 0, then this quantity will be 0, right. This first point. Second point, the electric field line is always perpendicular to the element dl of the equipotential surface. So, on equipotential surface, if you take a small element dl, so work done by external agent, we know if I multiply this to q naught, right. So, work done is equal to work done by external agent. If there is no change in kinetic energy, slowly we are doing that. So, work done by external agent is equal to negative of work done by field, and work done by field is force into displacement, right. As this quantity is 0, this quantity is 0, that means for this quantity to be 0, our movement must be perpendicular to the field, right. That means this dl vector, if this quantity is 0, this is nothing but mod E mod dl cos theta. This quantity is non-zero, this quantity is non-zero, but product is coming 0, that means this quantity will be 0 and this quantity can be 0 when theta is equal to 90 degree. That means the angle between electric field vector and dl vector has to be perpendicular. Electric field line is always perpendicular to the element dl of equipotential surface. Second point is clear. Now see next point. If we go along the field, right, you can see that the separation between equipotential surface will be smaller where field is strong. Just now we have seen because of the positive charge, we got equipotential surfaces something like this, right. So, when we are near to the charge, you can see these equipotential surfaces gap is less as compared to this gap, because here field lines are strong. So, as here field lines are strong, the gap between two equipotential surfaces, if I am taking difference same, for example I take 10 volt difference, so 10 volt difference, 10 volt difference, 10 volt difference. For example, if I take this as 50, 50, 40, 40, 30, 30, 20, so this say is 50, this is 40, this one 30 and this one 20. So, if I take same difference equipotential surfaces 10 volt, then see the difference here is same as difference here, but the gap here is less than gap here. So, where field lines are stronger, the gap between equipotential surfaces will be smaller. If E is strong, the separation of equipotential surface will be smaller. You can see in this example, right. So, this third point is also clear. Last point, we know that electric field line can never intersect each other, because at a particular point we cannot have two direction of electric field. So, if electric fields are not intersecting each other, the equipotential surfaces cannot intersect each other. Two equipotential surfaces cannot intersect each other. So, these are the four properties of equipotential surfaces. No work is done in moving test charge on equipotential surface. Next one, electric field is always perpendicular to the equipotential surface. Then third one, where field is strong, the gap between equipotential surfaces will be smaller. Last one, two equipotential surfaces can never intersect each other. So, these are the four properties of equipotential surfaces. Now, let us see some examples, right. So, two charges q and minus 2q are placed at distance 6 meter apart on horizontal plane. Find the locus of the point. Find the locus of the point where the potential has 0 value. That means I am asking locus of equipotential line of 0 potential, right. I hope you understood the question. We have got one positive charge and one negative charge, and question says draw line which will have potential 0, locus of all the point where potential is 0. Procedure we already discussed. So, let us take two charges, right, on xy plane, one is here, another is here, and let us take a general point P. So, this is a general point P where I can easily write the potential. What I write? Potential at point P. So, there are two charges in the system. This Q will produce potential that will be K Q divided by R1, this separation say R1, and another is minus 2Q. So, this second charge, as we are writing potential which is a scalar quantity, I already told you charge must be kept with sign. So, we will substitute minus 2Q, charge with sign, divided by R2, right. This we can simplify. So, Vp will be equal to K Q divided by under root x square plus y square. I am considering this point at origin 0, 0. So, this point is x, y. So, from here to here this gap is under root x square plus y square. Now, this is given 6 meter, right. So, this remaining gap will be 6 minus x and this is y. So, I can write, take this minus out, this is 2k q divided by under root 6 minus x whole square plus y square, right. This separation from point charge at distance r, we use the formula. Now, we can simplify this one. Requirement is we want potential to be 0. So, I will substitute 0 here. This k and q will get cancelled out, right. And you can see if I open this one, square and add, I will get this term on other side and square and add, that I am directly writing. Then I will get 6 minus x whole square plus y square is equal to 4 x square plus y square. Get this term on this side, squaring both sides and simplifying, you will get this term. Now, we can simplify, this will become 36 plus x square minus a square plus b square plus 2ab, right. So, this will become 12x plus y square is equal to 4x square plus 4y square. Let's simplify. This will become, if I transfer all these terms on other side, then you can see x square and 4x square will make it 3x square, and this will become 3y square. Okay. So, x over this y over, now this 36 on other side it will become minus 36 and this will become plus 12x minus 36, right. And if I divide the whole equation by 3, then I will get x square plus, get these term this side, this will be 4x minus, we are dividing by 3, this will be 12 plus y square is equal to 0, right. Now we can simplify, right. So, look at this one, I can make this one perfect square, I can convert this term into perfect square. What I need to do, I need to add and subtract by 4. So, if I add and subtract by 4, this will become, subtraction will give you 16 and 16 will go on other side, okay. So, there is less space, I will write it here, okay. I want to make this one as perfect square, so I will add and subtract. So, I will get x plus 2 whole square and then subtraction minus 4, transfer on other side, plus y square is equal to 16, right. So, this is the equation of circle whose radius is 4 square. This can be written x plus 2 whole square plus y square is equal to 4 square. So, circle of radius 4 and center at 0 comma minus 2, right. So, equation of circle is what? X square plus y square is equal to r square, where r is the radius of circle. This can also be written as x minus x naught whole square plus y minus y naught whole square is equal to r square. This is again the equation of circle whose center is at x comma y, x naught comma y naught of radius r, right. So, we are getting equation of circle. So, equipotential line on xy plane will be circle of radius 4 whose center is at minus 2. So, center at minus 2 will be somewhere here. So, center at minus 2, minus 2 will be somewhere here. From minus 2 I have to draw circle of radius 4, right. So, I hope procedure is clear. First I will erase this part, then we will talk about the result what we got. So, procedure was very simple. I require a particular equipotential line. For that I calculated the potential, substituted the requirement. After simplification we got this result. Now we are talking about result. So, the result says that equipotential line will be on xy plane, it will be circular whose center will be at minus 2 comma 0, minus 2 comma 0. So, x coordinate will be minus 2 and y coordinate is 0, that will be the location of center, and the radius of circle will be 4. So, from here this distance is 2, this distance is 2, another 2 will be somewhere here, okay, say somewhere here. So, I have to draw circle whose center is at minus 2 comma 0, for which the potential is 0. So, see, so it will be something like this. If I draw circle, it will be something like this, and this will have potential 0. So, this is the locus of all the point where potential will be 0, right. So, this is in 2 dimension on xy plane. Similarly, if I want to get the relation between x, y and z, then I will take, instead of x comma y, I will take x comma y comma z somewhere here, and then simplifying will give me the relation between x, y and z coordinate, right. So, what we got, locus of the point P is a circle with radius 4 and the center is minus 2 comma 0. I hope this is third example is clear. Now, let us see another. So, field in space is given and you are asked to draw field lines. So, field in space is given by this expression and you are asked to draw electric field line on xy plane, right. What is the basic concept of field line? So, if I say this is x axis, this is y axis, and we have got field lines like this, assume on xy plane I got field line something like this. So, according to field line concept, if I draw tangent at this particular point, I will draw tangent, then this tangent will give me the direction of electric field, right. That is the concept we discussed earlier. So, you can see that field at this particular point will have two components, one in x direction and another in y direction. And if I assume this angle to be theta, so what we can write, tan theta is equal to y component divided by x component. At this particular point, what is the y component? Y divided by x will give you tan theta, and tan theta on xy plane. If I extend this one, this angle is theta, tan theta on xy plane is nothing but dy by dx. On xy plane it is dy by dx, right. So, if I substitute the value of y component and x component and I simplify this equation, then I will get equation of field lines, right. If I take this example where this is y component, look at this one j, and this one is x component I, right. So, if I simplify, dy by dx is equal to y component from here y component is what, E naught x divided by x square plus y square. So, y component is E naught x divided by x square plus y square whole divided by, now I require x component. What is x component? I cap. In front of I cap what we have is this. So, minus sign E naught y divided by x square plus y square. Now, this x square y square and this x square y square will cancel out, E naught gets cancelled out, we are left with x by y. So, dy by dx what we are getting is minus x by y. If I just simplify, so this can be written x dx is equal to y dy with minus sign. And I integrate this one. Then this side I will get x square by 2 because this is indefinite integration plus some constant C1, and on other side I will be getting minus y square by 2, as this is indefinite integral I will get C2. If I simplify this one, C1 constant, C2 constant, I can bring it here, C2 minus C1 I can write another constant C. So, this can be written x square by 2 plus y square by 2 is equal to some constant C. So, this can also be written as x square plus y square is equal to some other constant. Right, x square plus y square is equal to constant, that is the field line pattern we are getting in space, right. So, what would be the pattern later we will see, but first I hope you understood the procedure. We use the concept of field line, the tangent drawn on the field line gives the direction at that particular point. If that is giving the direction, that means y component divided by x component is giving angle with x axis, y component divided by x component will be giving angle with x axis, right, tan of that. Tan theta on xy plane, that is nothing but dy by dx, right. So, simplifying this one, I will get the relation, integrating that I got finally this relation. This is the equation of circle, right. Now, I have to draw this. So, I will erase all. So, xy plane and I want to draw electric field lines, see. This is the equation of circle. So, that means electric field line in space will be circular. So, field lines will be something like this, right, all will have their center at origin. Now, I hope it is clear, right, all the circle will have their center at origin and the direction of field line, right. So, you can see that y component is x divided by x square plus y square E naught, while x what we are writing is minus E naught y divided by x square plus y square, because we are talking about the field and field will have direction. So, let us find out the direction. So, first quadrant x and y both will be positive. So, x will be positive and y will be positive. So, this quantity is positive, this quantity is positive, but with minus sign this quantity will be negative. That means at a particular point, at this particular point if I talk about, then x component for first quadrant as x and y comes positive, if I write positive x here, positive y here, with minus sign it is coming, then direction here will be reverse. So, this will be the x component, and look at the y component, x is positive. So, if you substitute positive, this whole quantity will be positive, this y component will be positive only. The resultant of these two will be in this direction. That means direction of electric field lines will be counterclockwise in a space. So, using expression I have drawn the line, and using what was given I am deciding the direction. Now, as I already told you that electrostatic field lines never form closed loop, they originate from positive charge and terminate at negative charge. Here we are drawing lines which forms closed loop, they are forming circle. That means this field pattern does not represent electrostatic field, it represents electric field, but it does not represent electrostatic field. So, in magnetism we will learn the cause of field might be due to charge or might be due to varying magnetic field. When electric field is produced by charge, then it comes in the category of electrostatic field, but when field is created by changing magnetic field, that is not electrostatic field and that is also not conservative in nature, that forms closed loop, right. So, this is the example of non-electrostatic field, or I can say non-conservative field. So, concept is clear, expression will be given to you. With the help of expression, if you simplify, then you will get the relation between x and y coordinate, that you can plot, and using that expression you can find out the direction, and by that we can plot field lines in a space, right. So, let us take one similar example, let us take the example of conservative field. This was the example of non-conservative field. So, non-conservative field we will talk later, but the procedure is same, whether it is conservative or non-conservative, the procedure of drawing field lines in a space is same. Now, question says the potential field depends on x and y coordinate as V is equal to x square plus y square, and you have to draw field lines on xy plane, right. So, one step is just added, like instead of giving field, now potential is given. So, from potential we know how to reach to the field. Formula is E is equal to minus partial differentiation of V with respect to x I cap plus partial differentiation of V with respect to y j cap. So, E I can write minus differentiation of this whole expression with respect to x. So, we have to assume y to be constant and we have to differentiate partially with respect to x. So, first term I will get this will be 0 and this will be 2x I cap plus, now differentiate the whole expression with respect to y. So, differentiating whole expression with respect to y, as x is constant, this term will be 0, now this term will be minus sign will come minus 2y j cap. So, if I simplify, then I will get E is equal to E vector is equal to minus 2xi plus 2yj. Now, from here on procedure is same. To draw field lines, what I need to write, dy by dx is equal to y component divided by x component. Y component is what? 2y divided by minus 2x. If I simplify, then you can see what we are getting. Get dx on other side. So, this will be dy by this y, 2 will get cancelled out with minus sign on other side. This is dx by x with minus sign. Now, again indefinite integral here and here, this will give you ln y and this will give you ln x. Ln y is equal to minus of ln x plus some constant, that constant might be log of something, right. So, I can also write ln constant. So, we can simplify this one, right. So, I will take the power up. Now, I will take the power up, this is y, ln y is equal to ln x to the power minus 1, x to the power minus 1 and this constant, right, ln a plus ln b formula we can use, that will become ln a into ln b into some constant, right. This ln will get cancelled out and you will get y is equal to constant into x to the power minus 1, and if I get minus 1 on other side, this will become x y is equal to constant. This is the equation of rectangular hyperbola. This is the equation of rectangular hyperbola. So, in a space, due to this potential variation, you will be getting rectangular hyperbola. Let us plot it. So, we have to plot rectangular hyperbola. Here it will be like this, here it will be like this, here it will be like this, here it will be like this. Similarly, we will have, so for different value of this constant, you will be getting different lines, right. Now, as we are talking about field, it will have direction. So, we have to decide direction here. So, to decide direction, as I already told you, look at this x component, this whole thing is x component and this whole thing is y component. In first quadrant, x and y both will be positive. So, when x is positive, if x is positive, x component is negative, y is positive, y component is positive. So, you will get, if you take point somewhere here, you will get y component positive, x component negative, right. So, resultant of these two will obviously be in this direction. Same way I can decide for this quadrant x is negative, y is positive. If x is negative, that negative and this negative will make it positive. So, x component will be positive. And look at this one, for second quadrant, y is positive, as this is y is positive, this whole thing will be positive, y component will be positive. So direction will be something like this. Same way I can decide direction here. So this is the way I can plot electric field lines. If I ask you to plot equipotential lines, what you need to do? This is the procedure to draw field lines in a space. How to draw equipotential lines? So if I substitute here, look at this one, here constant, this is the equation of hyperbola, x square divided by a square plus y square divided by b square is equal to constant. This is the equation of ellipse, right. If I put minus sign here, then this is the equation of hyperbola. Don't get confused between rectangular hyperbola and the hyperbola I am talking about. Rectangular hyperbola will be like this, right. Now I am talking about hyperbola. So this is the equation of hyperbola. Now compare this equation with this equation. Here x square is written, x square, y square, minus sign is coming in between, and we want equipotential line, that means potential is constant. So that means in a space you will be getting hyperbola. Now, so now I am drawing equipotential line. After drawing electric field lines, I am drawing equipotential line. So I am telling you the procedure to draw equipotential lines here itself. See, so the red one are equipotential lines and the blue one are electric field lines. So I will erase some parts so that you can clearly see. So what I am saying is, these red lines, these are these lines are equipotential lines. And the blue one, these blue lines, these are lines. So now I hope complete picture is clear. So procedure of drawing equipotential lines, whatever be the expression given of potential, put constant, right, and draw those lines. To draw field lines, first get the expression in terms of field, and then using the concept dy by dx is equal to y by ex, integrating that you will get the expression for field lines, right. I hope this whole concept is clear. So we talked about field lines in our third class, right, and today I completed the whole concept. So, potential concept and field line concept both got over. Now, let us see one point. I will take one example to make you understand one more point. So, this example says, you can read it. So, this example says कि I have one particle and I want to make it penetrate into a sphere up to radius r by 2, right. So, we got one positively charged particle and we want to make it reach to radius r by 2 inside a sphere. So, charge is distributed over space and there is no resistance offered by the sphere. So, when something gets into the sphere, so because of the material interaction, there will be some frictional force that is absent in this situation. So, only electrostatic force we have to take into account, and question is what should be the value of velocity, so that it gets up to that particular point. So, I hope you are able to see what is written in the diagram. I will just make it a little bigger. So, here this one is charge q and this one is mass m and it is projected with velocity v and it gets up to this particular point, right. This is what we want. So, I can easily solve this problem by applying work energy theorem. So, according to work energy theorem, work done by external 0, I am directly writing, right, work done by external agent 0. There I need to write change in kinetic energy plus change in potential energy. And change in potential energy can easily be written this way: charge into potential due to sphere, potential due to sphere final minus potential due to sphere initial. So, these are the values of potential created by the sphere at these 2 points, at initial point and final point, that I write here, plus change in kinetic energy. So, final minus initial if I do, finally it stops and velocity will become 0 and initially it is projected with velocity v. So, I will write half mv square. Right. So, requirement is v, only one unknown is v, right. So, only one equation is required, that is work energy theorem, I can use that. So, final potential, because of this sphere, final potential when particle is inside, we know the formula, that is k q divided by 2r cube in bracket 3 capital R square minus small r square. This is the potential inside. So, I am applying formula for inside potential where I need potential at distance r by 2. So, here I will write, in place of this r, I will write r by 2. Substituting the value here, I can put the value of V final here. Now, I require initial potential. As the point is lying, initial point of projection is lying outside, for outside we have potential formula kq by r, right. So, k q divided by r is the distance, that is given x, this is given x. So, I will write x here. Now, I will substitute initial potential here, I will simplify and I will get the answer, right. So, this initial potential I can substitute here. I hope procedure is clear, right. I just wanted to make you understand how to write the change in potential energy change in potential energy when we have one distributed charge and another point charge. So, if point charge is moving and distributed charge is stationary, then potential created by the distributed charge at the 2 points where point charge is moving, if we can write that and multiply it to the charge, I will get the potential difference, I will get the potential energy difference, final minus initial, right. So, this is the easier way of writing the potential energy due to distributed, potential energy due to distributed and point charge interaction, right. So, you can simplify, you will get this answer, you can verify simplifying this one, you will get this answer, you can verify, right. So, I hope we clearly understood potential concept, field concept, how to draw field lines, how to draw equipotential lines, and how to use work energy theorem, and how to apply Newton's law for all these situations, right. Now, let us move to next topic, electric dipole. So, electric dipole is nothing but the combination of two equal and opposite charges placed at certain distance, right. So, I will take one positive charge, one negative charge, and that whole thing I will call electric dipole. So, till now we were talking about a field created by a single charge or distributed charge, whole positive charge or whole negative charge, right. Now, we will take a certain situation where we have two charged particles in combination, where one is positive, another is negative, and they are of equal magnitude. So, what effect they will create in the space, what is the field created by them, what is the potential created by them, and what happens when they are kept in external field, right. So, all these questions we will answer, or we will try to answer in this part. So, nothing new we are going to discuss in this part, all the topic, all the basic concept we have already learned, concept of field, concept of potential, how to apply energy formula, everything we have learned. Now, those same thing we will be using in a new situation where we have charge system which consists two charges, one positive and another negative. So, a system, so we are talking about a specific system which will have two equal and opposite charges placed at a certain distance, that we will call electric dipole. So, two poles dipole, right. So, see, so one positive charge and another negative charge, they are kept at some distance d, this is called electric dipole, right. So, here we defined a parameter called electric dipole moment, this P. So, electric dipole moment of dipole is defined as charge into separation between them, charge into separation between them. So, magnitude of dipole moment is charge into separation between them. Now, dipole moment is a vector quantity and the direction of that is from negative charge towards positive charge. So, the direction of this dipole moment is negative charge towards positive charge. So, the direction of dipole moment is from negative charge to positive charge and the magnitude of dipole moment is charge into the separation between them, Q into D, right. So, I hope basic definition of dipole moment is clear. Dipole is nothing but a system of charges where we have got two charges, one is positive, another is negative, they have the same magnitude and one is positive, another is negative, and they are kept at certain separation, and the direction of dipole moment is from negative to positive, right. So, we use this dipole in different situation, but before getting into all, I can give you simple example like HCl molecule that behaves as dipole. HCl, electron affinity of chlorine is more as compared to hydrogen. So, these bond electrons will get shifted little towards chlorine, right. So, chlorine will get slightly negative charge and hydrogen will get slightly positive charge, right. So, this whole thing behaves as dipole, right. In physics we have direction from negative to positive, in chemistry we take from positive to negative. This is just a convention, it has nothing to do with why we are having a particular direction in physics or particular direction or different direction in chemistry, right. So, by convention we take in physics dipole moment direction from negative to positive. So, if I take HCl molecule, I can also represent this HCl molecule dipole from negative to positive, dipole moment, the whole thing can be replaced by a single dipole having dipole moment in this direction, right. Similarly, water molecule, let us see water molecule. So, electron affinity of oxygen is more as compared to hydrogen. So, these electron will get slightly attracted towards oxygen. So, these electron will get shifted towards oxygen and similarly these electron will get shifted towards oxygen. So, here because of this shifting you are getting slightly negative charge and because of this shifting you are getting again a slightly negative charge. Here hydrogen will have slightly positive charge and this hydrogen will also have slightly positive charge, right. So, because of this one, because of this combination it will have dipole moment in this direction from negative to positive. Similarly, because of this movement it will have dipole moment in this direction. So, if I ask what is the resultant dipole moment, as dipole moment is a vector quantity. So, because of this combination from negative to positive, one dipole moment will be in this direction and because of this one another dipole moment is in this direction, right. And if you add these two, the angle between these two comes 104. So, if I want to add, I can write net dipole moment is equal to under root P1 square, both will be same. So, P1 and P2, P1 is equal to P2 magnitude wise, right. So, I can directly write this as P. So, instead of writing P1 and P2 I will write P. P square plus P square plus 2 times P square cos 104 will give me net dipole moment. So, the resultant dipole moment of water molecule will be exactly at angle bisector in this direction. So, I can replace whole water molecule by a single vector which is representing the dipole moment this way. Instead of drawing this all, I can just draw this which is representing the direction of dipole moment of water molecule. So, chlorine, similarly water molecule, so they all have or they all are representing dipole. So, there are two types of dipole, one are polar and another non-polar. So, these are coming in the category of polar dipole. So, already polarity is there. Non-polar dielectrics are those where when you exert or when you apply the field they get the polarity. So, if molecules are having some initial polarity, the material is called polar dielectric, right, and if they are not having any initial polarity then it is called non-polar. So, when we will be talking about dielectric, then we will see that part, but for time being molecules behaves as dipole. So, these are some practical examples. Now, let us see some example to understand the dipole moment. So, you can see that this system contains 3 charges, plus q and here minus 2q. If I ask what is the dipole moment of this arrangement, so what I can do, I can break this minus 2q in 2 parts, minus q comma minus q, right. So, here 1 minus q, this can be written, minus 2q can be written this way, right. Look at this combination, and this combination. So, you can see this combination is behaving as one dipole and this combination is behaving as another dipole, right. So, as this combination is behaving as one dipole, I can represent this one as dipole of magnitude or dipole moment of magnitude q into L, charge into separation. Similarly, this can be expressed charge into separation, magnitude I am writing, and as this angle is 60 degree, I ask what is the resultant resultant dipole moment, then we can add these two vectors. So, net dipole moment of this arrangement will be under root q into L whole square q into L cos theta. Here theta is equal to 60 degree. So, here I can write 60 degree. So, simplification of this one will give you net dipole moment of the arrangement, that is coming cos 60 degree 1 by 2 and 2 will get cancelled out. You can see 3 inside and take q L whole square out, then you will get q into L under root 3. So, this whole arrangement can be represented by resultant of these two. So, resultant of these two will be something like this. This is root 3 into q into L. This is net dipole moment. I hope this example is clear. Let us see one more example, right. So, instead of taking 2 point charges, what I have done, I have taken one point charge and another distributed one, which is distributed over ring. So, charge is distributed over ring, and I am asking what is the dipole moment of the system. Now, you can break this q into small part dq, and those dq will be making combination with the dq on the ring. If I take a small element at an angle theta, which is subtending angle d theta, then you can see here the charge on this element, if I say dq, so this minus dq, and if I take a small part of this one, that is plus dq, these two are making a dipole, right. So, what I can do, the direction is from negative to positive, right. So, I can draw it this way dp. which is subtending angle theta here. So, you can see it will have two components, one in x direction and another is y direction, right. So, this can be written dp x component as dp cos theta and dp y component as dp sin theta. If I integrate, then I will get the result. If I integrate, I will get net dipole moment x component and here I will get net dipole moment y component. So, dp is what? dq into r, charge into separation dq, this is dq into r into cos theta, right, and this dq can be written charge is distributed over length q divided by pi r into r d theta, while linear charge density into length will give you charge. So, if I substitute this value here, you can see it is nothing but integration of cos theta, limit from 0 to 2 pi, integration of cos theta will give you sin theta, right. So, putting limit 0 to pi, this whole quantity will be 0. So, this whole quantity will come 0 when you put the limit. Similarly, here you can see this dp can be written, I am directly writing right, this is dq only into r into this sin theta integrating from 0 to pi, integration of sin will give you cos and when you integrate from 0 to 2 pi you will get 2, right. So, we are not getting any x component, we are getting only y component. So, once you simplify you will get this result, right. So, 2 rq divided by pi j cap. So, after simplification I will write it here, that is 2 rq divided by pi, right, only negative y direction. So, I hope concept of dipole is clear. So, tomorrow we will talk about other cases associated with a dipole. So, I hope you enjoyed today's class. So, thanks for watching.